Hi everyone. This time we're going to talk about the Doppler effect. Now, the Doppler effect is defined as the change in the frequency of a wave due to the relative motion of either the source or the observer of a wave. It's impossible to describe the Doppler effect without making funny noises, so here we go. Let's say you have your back to a street and a car goes by and you hear it go vroom. What happens is as the car is approaching you, the frequency sounds higher in pitch. And at the moment that the car passes by you, it sounds lower in pitch. That change in frequency on approach and then after it is moved away, that is referred to as the Doppler effect. This happens not just with sounds, it happens with light. It actually can be seen in water waves and other sorted waves. But let's spend some time explaining how this occurs. So let's say the source of the wave is moving towards you. So let's say there is a railroad clangor and it is producing some sound waves. So every few moments it is producing a sound wave that is clanging and going through in space. And the train is safely out of the way, and so you are about to drive over the railroad tracks with your automobile. So as the wave is approaching you, you are also approaching the wave. So you are actually encountering these waves hitting you in your cute little ears a lot more often than you would if you were standing still. So what happens is the frequency, how often the waves actually hit your ears, is a lot higher as you approach the source than it would be if you were just standing still and the waves were coming over you. So the velocity of the sound waves plus the velocity of the observer is going to make the frequency higher than normal. And it doesn't matter if you're moving towards the source or if the source happens to be moving towards you. Now, what about the opposite situation? You're moving away. So let's say the railroad clangor is still here, periodically putting out its little clang, clang, clang noise. But now you have crossed over the railroad tracks. You are driving away from the source, and the sound waves are traveling at their same speed of sound. But every time between each sound wave, you are traveling a little bit further away from the source. And so the waves have to travel a little bit further between clangs in order to hit you. In order to do that, what that means, because there is a greater space of time between each wave encountering your ear, the frequency is going to be lower. And you're going to have that vroom, that lower frequency, that lower pitch, whether you're moving away from the source or if the source is moving away from you. Now, where is this actually used in the big world? Well, there's a whole bunch of places. And one of the places it is used all the time is police radar guns. If you have ever been the proud owner of a police radar ticket, this is how it works. The police officer has a radar gun that is going to shoot electromagnetic waves at your vehicle. They're going to bounce off your vehicle, return to the sensor in the automobile of the police officer, and within it, it is computer programmed to do the math to account for the speed of the waves, about the speed of light, and deal with the additional speed of your car. And it will back calculate the speed of your car, display it on the radar screen, and some of you get a smiling happy face and some of you get a ticket, and it happens, unfortunately. There's also Doppler weather radar. Now, when I was a kid, long ago and far away, there was no such thing as Doppler weather radar. Now, in the modern age, this is the only kind of weather radar some of you have ever grown up with. When I was a child, the only kind of radar that existed looked like this, meaning that the weather stations, they could send out radar waves and they would bounce off of a cloud and come back, and the weather forecasters would say, hey, cloud, cloud, and they would know where the clouds were, but they had no information about the speed of the clouds. And if you don't know what part of the cloud is going fast, what part of the cloud is going slow, then you cannot forecast in great accuracy things like tornadoes. See that cute little hook? That is a very good radar signature that indicates that might be a possible tornado. And with modern day forecasting with Doppler weather radar, tens of thousands of people's lives have been saved due to good weather forecasting with the addition of being able to add speed to the weather forecast of impending storms. Doppler effect is used in ultrasound machines. Ultrasound machines can be programmed so that the color pattern for red or blue is totally determined by the ultrasound operator, but it can be determined for fluid flow towards the transducer or away from the transducer, and it can indicate if you've got blood going into the various chambers of the heart or out of the various chambers of the heart. Renal, of course, means kidney, fluid flow in, fluid flow out. And so something like ultrasound, instead of just being a static, flat, non-moving picture, you now can actually see fluid flow into and out of organs, which is very wonderful for diagnostic tools. One of the other places you may hear Doppler discussed is in astronomy. Early 1900s was the first time, a little over 100 years ago, that we realized that there are other galaxies. And today we know there are billions of other galaxies out there. And astronomers have realized that almost all of them their light is shifted towards the red end of the spectrum. What do I mean by shifted towards the red end of the spectrum? Well, if you look at the hydrogen gas, most stars contain a lot of hydrogen gas, and the spectra produced by hydrogen and helium might look something like this if the sample is sitting on your laboratory bench. Well, if the source of that light is moving away from you, all of the colors are going to be there. They're just going to be shifted a little bit off from the right locations. It's there, but it's just a little bit wrong in number, and they're all proportionally the same amount wrong. If the source is moving towards you, everything is going to be shifted a little bit towards the blue end of the spectrum, and that all same thing, all the colors are there, they're just shifted the same amount wrong towards you if it's blue shifted. Red shifted means away. Well, what was discovered is that when we look into distant galaxies, many of them, almost all of them, vast majority of them, are redshifted. So what does that mean? Well, a gentleman named Edwin Hubble, about 100 years ago, determined that all these galaxies were moving away from us, as if we were the center of the universe. And all of these galaxies are redshifted away from us in every direction we looked in space. And people were going, what the hey, how come this situation exists? Well, that became the beginning of what we know today as Big Bang theory, because if the entire universe is moving away today, that means at some point in the past, if you run the movie backwards, it was all closer together and everything was crunched down into a tiny, tiny, much smaller space, and that the universe has been expanding in all directions ever since the beginning of space and time. Weird and crazy, wacky things, but that observation occurred because of the Doppler effect. Now, this is the Doppler equation. Different textbooks will give it to you in different forms. Some textbooks will give you a different calculation if you're moving towards the source or the source is moving towards you. I'm not that smart. I like one equation, one all-purpose Doppler equation, and we're going to just tweak the equation for the situation. So write this down, and then we're going to go through all of the bits and pieces. So FO is the frequency observed. This is the frequency. If you're talking about sound, this is the sound you hear. Fs, this is the frequency of the wave source. V is the velocity of the wave at rest. So the velocity of sound with no motion overlaid, or the velocity of light with no motion overlaid. VO is the velocity of the observer. and Vs is the velocity of the source. Now, frequencies are all in hertz, and all of these velocities are in meters per second. Now, what gets wacky are the signs. You see the signs here and there? The top set of signs are plus, minus, and the bottom set of signs are minus, plus. Now, why in the world are there a set of signs on top and a set of signs on the bottom? You use the top set of signs if there is movement towards. So either you're moving towards the source or the source is moving towards you, and use the bottom set of signs if things are moving away. Now, by using this, there is no need to change the signs of any of the velocities if you are moving away or towards. And the reason I mention this is long ago when we did kinematics, if we had motion in two different directions because of the vectorness, we had to call one positive and one negative motion. We do not have to do that with the Doppler effect if we pay attention to this plus minus on top, minus plus on the bottom. So the only way to really have a good understanding of what this Doppler equation means is to do a couple examples. So we're now going to stop and do a couple Doppler equation examples. So I will meet you at the examples, and we'll see you there in a minute. Bye-bye.